Hello all, good morning. I'm Kumaresh from Bosch. I'm here to talk about using simulation to have a robust hazard analysis and risk assessment. So let's start with an example, what it is in the autonomous world. Here is a picture where you can see water droplets accumulated on the windshield. And if we have a camera-based system for image perception, sometimes these water droplets can be misinterpreted as obstacles on the road, and the system can react to it by causing aggressive braking, which can result in rear-ended collision or loss of stability. This is quite common in the autonomous world. So the traditional HARA, which we do as per ISO 26262, is confined to electrical and electronic faults. But when we move into autonomous world, we have functional insufficiencies like this that can cause hazards, which we have to import into our traditional hazard analysis and risk assessment for effective safety concept. So what are the new vectors that are influencing HARA in the autonomous world? First is fault perceivability. Now, based on SAE levels, we might have a driverless system, which means the controllability rating that we give in the risk assessment varies a lot based on the SAE level that we have in autonomous. So we have to revisit the existing HARA, even though the components remain the same from the traditional vehicle. We might have to come up with new safety concepts needed for the autonomous system. Next, we have to focus on sortive hazards. The above mentioned example is one case where it was functional insufficiency, but we have to look into functional insufficiency and also foreseeable misuse. Then we have to look into the cybersecurity threats, the threats that can impact the integrity of the safety functions. We have to import it into HARA. And the last one is the minimal risk maneuver. We have to identify what is the minimal risk maneuver, what are the triggers for it, what are all the vehicle specific thresholds, the safety thresholds, time available for reaction in the MRA. So how does the HARA process look like? This is the one from the traditional ISO 26262, where we have functions which from which we derive the malfunctions due to electrical faults. We derive the hazards out of it, and then we make a risk assessment to come up with the ASIL rating and the fault tolerant time interval. If we move into the autonomous world, we have other vectors. As we discussed, we have to include the cybersecurity threats, the SOTIF functional insufficiency. We have to adapt our situation catalog to the ODD of the intended vehicle. So we have new players coming in the HARA for the autonomous world. So what is the challenge here? First challenge is how we reuse the situation catalog based on the ODD of our vehicle. How do we rerun the entire hazard analysis that we have for the new ODD that we intend to? This is one problem that we often see. Then the second one is how do we justify the severity and controllability rating in our hazard and risk assessment? And the third one is how do we derive the safety thresholds for our vehicle behavior? So this is where we started debating the use of simulation software, which can kind of automate this risk assessment and come up with a very reliable severity and controllability rating. So what we did is we fed all the situations from our risk assessment into a vehicle model. It's a model-based simulation. And we started estimating what is the time available for collision and what is the delta acceleration during collision. From time available for reaction, we can directly relate how controllable the system is. And also from the delta acceleration, we can understand what kind of injury is possible and what kind of severity should be chosen. So how we related is the delta acceleration directly corresponds to severity. The time available for reaction directly relates to the controllability. And finally, we get the safety thresholds for the vehicle from the simulation software. Let's see an example how it worked for us. There's a safety goal, prevent unintended vehicle motion. In the scenario, downhill, vehicle is on the slope. There's enough space to roll for the vehicle and probably collide with the pedestrian. The system we are focusing is the park lock. The failure we are focusing is unintended disengagement, and we import the vehicle parameters into the system. Now we try to simulate this for two different road gradients. first we started with 10%, which is quite common in areas like Texas, where we saw a reaction time of 1.1 seconds. But the moment we want to take the same vehicle, put it into different region with different ODD, let's say San Francisco, it has a road gradient up to 40%. So we try to simulate it for a different road gradient, let's say 20%, then we see a reaction time of 0.74 seconds, which means there's a 30% reduction in reaction time when we move from 10% road gradient to 20% road gradient. What it means is I design a system for a particular ODD for a particular region of one road gradient, and I just port it to another one. I have to redo all my safety analysis, come up with the new safety thresholds and additional safety concepts probably for it. So what is safety simulation doing here? It lays a strong safety foundation right from beginning of the project. Right when I don't have a prototype or I cannot test it in the particular field, I can start using a model-based approach to come up with the realistic figures for my safety concepts. Then I can have a safety insight for the intended vehicle for the intended ODD. Also, I can make this entire HARA objective driven rather than subjective, where I can derive the characteristics for my particular vehicle, parameters. So yeah, thanks. And please, I'm happy to answer the questions. Thank you.
This saves us time for the breakout. So any questions?
There's some general questions. So why your system have like an AI component, right? So just say making through some model for process all the way to the job. And how do you use this framework? Like every time the data training data is different, or every time I rerun the model training, whatever, things have become different.
Yeah.
And I really cannot classify it as like a gradient change or something. I can, as a developer, even I'm pretending I'm a developer, I cannot have. So how does this framework work in that situation?
I mean, we have a situation catalog for your hazards that is critical enough, right? So we would rerun this situation catalog against the new vehicle parameters, and then we'll try to assess how much time we have for collision or what should be the fault tolerant time interval for your system.
Okay, I think my question is more like at the very beginning. I mean, based on your example, I know the gradient is one key component. If that changes, I need to redo the cases.
Yeah.
But if the software itself has some like uncertainty or something I cannot fully understand, so I don't have a gradient as a metric I'm looking at. How do I figure out which one I should look at? So that if that changes significantly, I need to redo the safety or the analysis.
I mean, we are talking about the effect, right? The hazards and what is the impact of the hazards in different scenarios. Which software component causes that effect? That is in the next phase in the functional safety concept or technical safety concept. Maybe we can discuss further later in detail how we can approach it. But one thing is this has to be a continuous process. I mean, in ISO 26262, we always had it only based on electrical and electronic faults, so we can do it single shot. But now this cannot be done just once. We might have to rerun it again and again based on new scenarios that we identify in the sort of. Yeah. Got it.
I have a question on this. So you mentioned autonomous vehicles, right?
Yeah.
Yes, there are EE systems over there, but algorithm, machine learning will come also. There are other standards like I think 8800 for AI safety.
Yeah, that's coming up. Yeah.
That's coming up, right? So and then you have cybersecurity for 21434, right?
21448 so yeah.
You name it, right?
Yeah.
So I saw two standards coming in this framework, right? So are you planning to add more?
Yeah. I mean, if I get to know more about 8800, then I'll also add it into the track.
Yeah, because those are like algorithmic.
Yes. Yeah.
Question. So I guess I'm still a little bit kind of confused. So like, what is the tool? What is the simulation that's being form? Like, what is the tool assessing? Like, is it assessing the new FTTI or the concept, or I guess can you go a little bit more into detail, like how the tool actually performs the assessment, or what is the end result? Is the end result a change to controllability, or what is the effective tools?
Okay. So as a part of risk assessment, we come with severity, controllability, and exposure rating that finally decides the ACIL rating. Right? Severity talks on American Injury Scale. What is the possible injury with that particular collision or something like that. Today, without vehicle tests, it's hard to decide what kind of injury is possible with what kind of collision, or sometimes it becomes subjective. The same goes with the controllability rating. As per the standard, we talk about 90% of the drivers able to control it, or 99%. But how do we decide how many percent is able to control it? And often when we do this analysis, we are in preliminary phase where we don't have the real vehicle or the real scenario where we can test it. Then we were thinking for ourselves how to make it logical, how to come up with a reliable severity and controllability rating. And that's where we started using simulation, even within ISO 26262 framework, before we went into the autonomous world. So what we do is we try to apply the maximum torque in our simulation model that is possible for that particular vehicle, for that particular mass, dimension, and so on. And we try to assess how much time it is there for collision. Then we know, say, for 1 second, how many percent of drivers can react to it, or so on. Maybe we do it for one use case, we can test it in the real vehicle, how many people can react for 1 second or 2 seconds or something like that, and translate it back to all the scenarios here in the situation catalog. Usually you have hundreds of scenarios per safety goal, where we cannot run for each and every scenario a vehicle test, but we can have a reliable results from the simulation too. That was the starting point. The next point is the FTTA. When we design our system safety mechanism, we have to say within what time the system has to react, like within 1 second, 0.5 seconds. That decides the controller throughput, the speed, and so on. So we need a very good rough figure for our system so we can purchase the appropriate controller. We have to also maintain a balance here, right? If I am conservative here, I'll end up buying a costlier controller, which is not necessary for my system. If I am not conservative, sometimes I might miss something and find it at later point of my project where I have to rework everything. So simulation gives a very good ballpark where I can start and probably maintain this balance in my decision making of the project.
Sorry, small question. So for determining controllability, is it as the number of people that can react in that amount of time, you rely on human factors? That study to perform them yourself, is like, or is there like maybe publicly available information sources that may contain some of that information? I guess can you comment on that aspect?
Yeah, but again, the situations are different, and sometimes we might need a specific evaluation for our vehicle for that particular situation. Then simulation software helps us a lot in those cases. What we have seen is all the general cases we have public study, but all these new things like autonomous driving, we might not have much information, and we might have to start off with the simulation for ourselves.
And what is that simulation tool?
It's what we have developed for in use within Bosch.
Oh, it's an internal tool.
Yeah, it's an internal tool.
Well, that's what they were after. What is, yeah, it's all about simulation, but what are we talking about here?
Is it going to be a product?
Yeah. We are thinking about a web portal in future where customers can, feed in the vehicle parameters and get the simulation characteristics output themselves.
Yeah, one question on the situation catalog. Do you also have these mechanisms that allow you to discover new situations that you have not thought about?
Yeah, I mean, from the field, whatever we observe, we keep updating our situation catalog based on the feedback.
Okay, based on that. Not something with reasoning AI that will generate potentially hazardous combinations of states of subsystems, and then basically take that from the unknown to the knowns.
That's a very interesting thought process.
Yeah.
Actually, we were debating a lot about using Gen AI for creating these situations, but again, the reliability of its output is a big question at the moment. So we don't want to include it directly within the product.
All right.
Yeah, but that's a very good question.
Yeah, interesting.
Yes.
I just wanted to comment, all models are wrong, but some are useful. And the same with the simulator, so you cannot use much of simulating for this kind of simulations.
Curious on the ASIL rating.
Yeah.
When it comes to autonomous autonomy,
Mhm.
do you see variety in ASIL or everything falls into ASIL-D?
You can still see varieties of ASIL, but again, it depends on the subsystem.
A lot falls into
Yeah.
ASIL-D when it comes to autonomous.
Yeah, because it directly goes for C3 controllability rating. Yeah, sure.
Okay, I think let's thank
Yeah.
Kumaresh, and let's welcome our next
Thank you.